Thank you all for coming. It's a great pleasure to be here and to give this lecture on massive MIMO. So I guess we'll start with the fact that there are three main ways of improving wireless communications. Either we densify the network, putting the access points more and more closely together. And that seems to be a popular approach, also known as deployment of small cells. The difficulty with doing that is that putting access points closer and closer together is never really going to do away with the interference problem. In fact, most wireless systems are limited by interference. And in fact, the closer we put the access points, the worse we make the interference problem. And the reason is that the path loss models change when the distances become shorter. So if you have large cells, they might have a path loss with exponent 3 or 4 or even 5 or something like that. When you bring the access points closer and closer, eventually you're going to have line of sight to everybody. So you're going to have like a path loss exponent of 2 or even below that. So densifying has its very severe limits. The other kind of main approach of improving wireless is to increase the amount of spectrum that we're operating in. And that's obviously very popular as well. I mean, for 5G, then there's a lot of talking about its millimeter wave frequencies. And we're going to hear more about those, I guess, tomorrow lecture. So, in fact, there seems to be a significant amount of new spectrum that will be set aside for 5G services. And those are all high frequencies, where propagation is a lot different than from lower frequencies. Propagation is more like line of sight, or line of sight with a few specular reflections and like that, which has its own problems. So today, I mean, we're going to focus mostly on operation at low frequencies, say below 5 gigahertz. So the third way of improving wireless is to deploy more antennas at the base stations. And that is what's referred to as MIMO or massive MIMO technology. And that is going to be the subject, in fact, for the whole day. So the way we're going to structure today is that I'm going to speak here in the morning before lunch. And we're going to have a break. I think we're running a little late, so I'll try to speed up, So we'll have a coffee break, I think in an hour at 11. And then we're going to have an hour and a half with me until lunch. And I'm going to cover mostly basic topics on massive MIMO. And then after lunch, my colleague Emil Björnsson is going to give another 3-hour session. And he's going to cover more advanced topics. So that's how we split this. And also, I'd like to underscore the fact that, I'd like to make this an interactive experience. So if you guys have any questions along the way, then just interrupt me and ask. So, all right, massive MIMO in its canonical form is cellular massive MIMO. So the geographical area that we want to cover is partitioned into cells, and every cell is served by a base station. And these base stations here then, speaking of massive MIMO, they have a large number of antennas. We say large, we mean like 100 or maybe 200, possibly more even. And every base station multiplexing to a number of terminals at the same time. Large number at the same time, that's the whole point. So you want to multiplex something like 10 or 20 or even 30, or possibly even more. And importantly, these cells here, these base stations, they operate autonomously. So there's no cooperation in between of the base stations, other possibly for slow tasks. Slow tasks in massive MIMO include the allocation of pilot sequences, for example, and the power control. Power control in massive MIMO is a slow time-scale activity. And for that purpose, these base stations might help each other a little bit. But fundamentally, all the coherent signal processing is done per cell inside of every base station here, and that's it. So in that way, cellular massive MIMO is entirely scalable. I mean, you can just add more and more cells, and that's it, right? The processing scales with number of cells. Although we return to the processing that goes on inside of each one of the base stations here. All right, so the preferred way of operation of a massive MIMO base station is in time-division duplexing, or TDD mode. And the reason for that is that in TDD we can exploit reciprocity of the propagation channel. Reciprocity refers to the fact that the channel responses on the uplink are identical to the channel responses on the downlink. So in TDD, we should think of TDD operation as like this, that we have a time frequency plane like this, and the time frequency plane is chopped up into blocks, okay, sometimes speak of frames, but fundamentally, it's just looking at the physics. We split this time frequency plane into small parts here, small chunks here, that we call channel coherence intervals. Okay? Channel coherence interval is the time frequency space over which the channel substantially acts as a static linear system. So the channel just multiplies whatever you transmit in such little small red space here. The channel just multiplies that with a constant scaling, amplitude scaling and phase rotation. Every such coherence interval, it has a time duration which is equal to the coherence time of the channel. Yeah? And it has a bandwidth which is equal to the coherence bandwidth of the channel. We'll be returning to these quantities a little later on when we talk more quantitatively about performance analysis. And every such coherence interval in turn is split into two parts, an uplink part and a downlink part. Yeah? In the uplink part, then all the terminals that we want to offer service, they first send pilots, all of them at the same time. Okay? And these pilots are mutually orthogonal in between of the terminals, and that's important. So the pilot sequences inside of a cell do not interfere with each other. They are orthogonal. And subsequently to that, the terminals send payload data in the uplink. Yeah? And the base station uses all this information gathered on the uplink to estimate the channel responses between each one of the terminals, each one of the base station antennas. And then it decodes the data sent on the uplink. So they all transmit simultaneously in the same coherence block here. That's important. In fact, that's the whole point of massive MIMO. It's all going on at the same time. It's called spatial multiplexing. We multiplex them at the same time. They have different spatial signatures, different channel responses. So now, these estimates of the channel responses gathered here from the uplink pilots, those are also legitimate estimates of the channel responses in the downlink. So in the downlink phase, then the base station can pre-code or beamform payload data to the terminals. Okay, every terminal gets its own data, and that pre-coding uses it's based on the channel estimates that we learn on the uplink, and this is where the reciprocity comes in. So the fact that the uplink and the downlink channel responses are equal, so that channels estimated in the uplink are valid also for the downlink. Yeah. All right, optionally, one can also send pilots in the downlink, beamformed pilots. So that would mean that alongside with the data that we beamform to the terminals here, we would send some pilot symbol, okay, so that the terminals could also learn something about the channel response. That turns out to be unnecessary in practice. So that's why I marked with a cross here. I'm gonna touch upon that topic slightly later on here. So for now, just remember that there is the possibility of sending such downlink pilots, but we might not want to do it, okay? Yes?
The uplink pilots, where are they between the uplink data and downlink? Normally they should come before the uplink data.
Yeah, so I mean, so the question is whether the order here is that we start with the data and then the pilots. In practice, I mean, you probably want to spread the pilots all over here. You want to spread the samples, interleave the samples, pilot and data samples. But there might also be a point in putting the pilots as close as possible to the switching point here, because in practice, the channel, this is like an information theoretic model, right? Known as the block fading model, where we pretend that channel is static during every coherence block. And then next coherence block, it changed to something completely else. Yeah, but in practice, what happens is the channel is like slowly varying like this. So it's almost constant within a block, but it does vary a bit. And then it would be advantageous to put the pilots as close as possible to the middle here, because we estimate channels based on those pilots, then we're going to kind of extrapolate a little bit to the left, a little bit to the right. So this is a cartoon that I sketched together here. Yes? So the question is, if I understand well, whether the okay, so I think the question is whether the terminals here send, whether the pilots all have the same power in the uplink. So in my analysis today here, we're going to make the assumption that every terminal uses maximum possible power for the pilot sequences, okay? And that might not be necessarily the optimal thing to do in practice. So a lot of tweaking that can be done here to improve things, okay? But it's a baseline assumption, that's what we're going to start with. So every terminal uses maximum possible power on their pilots. However, those pilots do not interfere since they are orthogonal, so it's no problem. But in principle, the energy spent on those pilots could be spent on something else. So that's the trade-off there, right? However, the payload part, both in uplink and downlink, is power controlled to mitigate near-far effects and so forth. So we'll return to it a bit later. Yeah. Okay, great. All right. Okay, so in massive MIMO, the processing at a base station, the pre-coding and the decoding, that takes place using linear signal processing, which in practice means that we're looking at the downlink here now. Whatever is emitted from any of the antennas at the base station will be a linear combination of the symbols destined for the K terminals that way. So K is the number of terminals here. So destined for the terminals that they were multiplexing to, okay? So that's what linear signal processing means. And there are two kinds of linear signal processing that are particularly useful and popular. And those are maximum ratio processing and zero forcing processing. With maximum ratio processing, the weights that are applied in the linear combination here, those weights are given by the complex conjugate of the channel responses between the antennas at the terminal, antennas at the base station and the terminals. Okay. In practice, you'd have to use an estimate here. So will a G here be a matrix that contains all these complex valued coefficients between, say, M is the number of base station antennas and K is the number of terminals. So it'll be like an M by K matrix. Okay. So with maximum ratio processing, the weights that are applied here, you take the symbols that are destined for the K terminals. Okay, those are multiplied by weights. Then with maximum ratio processing, those weights are just the complex conjugate of the channel coefficients. And in practice, those channel coefficients are not known to anybody, okay, a priori. However, the base station will estimate and learn them here from the uplink pilots. So in practice, you would plug in an estimator. So it'll be something like a G hat, okay, where hat stands for estimate. So the physical effect of maximum ratio processing, looking at a downlink here, is that think of beamforming to a single particular terminal here, is that when you look at the wave field that the array generates, that wave field will have a peak in power at the particular point where the terminal is located, and then it will be much lower everywhere else. Yeah. So that's maximum ratio. And the other kind of canonical way of doing the linear processing is zero forcing. And with zero forcing, these weights here in the linear combination, those are given by the pseudo inverse of the channel, this matrix, M by K matrix that contains the channel responses. Okay? And the physical effect of that is that we're going to see a concentration of received power at the point where the terminal in question is located. Okay, so we're generating now, looking at the what's going on for one of the particular one of the terminals. We're going to see that terminal would see a concentration of power where it's located, with its own data module. I mean, its own data sent there, right? And then at the same time, that zero forcing precoder is going to place spatial nulls at the locations where all the other terminals are. Yeah. So when you look at this picture here, you might say that, hey, wait, if you can do this stuff here with the nulls, placing these nulls, then why would you ever consider doing that maximum ratio up here, which doesn't place any nulls? Yeah, so maximum ratio is going to create a lot of interference in between of the terminals. I'm for sure going to send a lot of power that ends up being concentrated where the terminal I'm targeting with is located, but I'm also going to spread around interference that others are going to hear. So why would you ever consider doing maximum ratio when you can do zero forcing? Well, one reason is that the processing is a little more complicated. It involves computing the pseudo-inverse. The pseudo-inverse, if you're multiplexing to 10 terminals, you would have something like, this would be a 10 by 10 matrix that you would have to invert. Turns out that's not really a big deal, okay? So, doing the zero forcing is not really computationally a lot worse than doing the maximum ratio. But there's another reason that reality is not fully as good as the pictures here suggest. And those reasons are the fact that In practice, you would have to replace your G here with an estimate. Yeah? Whenever you take this pseudo inverse and you replace G with an estimate, you're going to perturb the location of these zeros here. So in practice, this ability of zero forcing to place spatial nulls and suppress interference will be severely distorted by the fact that we don't know G perfectly. We only have an estimate. And in fact, the time that we have available to learn this estimate is quite short. It has to be learned from these uplink pilots here, and it has to be relearned in every channel coherence block. And the time that we have to do it might be like a millisecond or so. So in fact, these estimates that we plug in might be rather inaccurate in practice. So that's one reason that zero forcing is not as good as the picture suggests. The other reason that in practice zero forcing is not as good as it suggests here is that we're going to have a lot of interference that comes from other cells. Yeah, I mean, zero forcing might be able to kill off interference that comes within the home cell, but it does nothing in its original form to kill off interference that stems from other cells around us. I mean, it is possible to do more advanced signal processing. I think Emil in the afternoon is going to talk a little bit about that, but in its basic form, it doesn't. So, all right, great. So, yeah, okay, yes.
The maximum ratio we have also channel estimate, right?
Yes.
So in both cases we have an estimate. We don't have the relay.
Yeah. Yeah, right. So the question is, I mean, obviously in both cases, we're going to plug in an estimate here, right? So you're going to perturb, maximum ratio, you're going to perturb the location of this peak a little bit. Yeah, so you lose a little bit because of that. But with zero forcing, you're going to perturb that peak here a little bit, but you're also going to perturb the location of the nulls. And that's much worse because the nulls are so sharp. You can see them in the picture here. So you perturb them a little bit and they don't help anymore. Right? So, yes? Yes, that's correct. I mean, because now this is, think of this as this is all per coherence block processing, right? So you could think of that as like processing in the frequency domain. You take like every subcarrier independently, you do something. So if you work in the frequency domain, and you take the complex conjugate, that's equivalent in the time domain to time reversing. So an equivalent way of thinking of this maximum ratio stuff that's going on here is time reversal processing in the time domain instead. So yeah, that could be done, yeah, sure. Yes.
In case in which we won't have access to the estimate to the Chalmers we measure in case of hybrid architectures.
Oh, that's a good. I think that's. So the question is, if we don't have if we aren't able to measure the complete responses here on the uplink, then what do we do? I mean, if, for example, if there's some more complicated hardware that entails hybrid beamforming or something, and then this doesn't work as it's stated here. I think, in fact, we'll hear about that like tomorrow and Wednesday. Yeah, I think Nuri is going to talk about that. Yeah, when you have these hybrid architectures. Yeah. All right, great. So this is just to amplify or make the point that if you have a line of sight environment, then all this beamforming or multi-user MIMO precoding, it really takes the form of forming beams that point into particular in particular directions in space like this, into angular directions. But most of the time we don't have line of sight. And in that case, one way of thinking about the beamforming or the precoding is that the antennas here in the array, they all emit wave fields, okay? And these wave fields are created such that they will add up constructively at the locations where the terminals are, and destructively almost everywhere else. So maybe a better name, I mean, a lot of people say beamforming here, or I say processing here, but a lot of people say beamforming. But actually a better name is MIMO precoding, because beamforming leads us to think that we're forming beams into like narrow directions in space like this, which only has any sort of sound interpretation if there's line of sight. All right, so pretty much everything I say here today is, generally applicable to massive MIMO regardless of the carrier frequency. But the preferred operation of reciprocity-based MIMO is really below 6 gigahertz. And that's because at those carriers, then radio waves propagate through objects very well. I mean, they go through walls and to some extent through windows and so forth. They also bend well around corners. There's a lot of diffraction going on, so we very seldomly have line of sight. We might have sometimes a line of sight component, but most of the time, not. And we rely on kind of creeping and diffraction phenomena. We have a fairly long channel coherence. So even at highway speed, high mobility at highway speeds, we might have a coherence time at these frequency bands, which is in the order of 1 or a couple of milliseconds, which is substantially long, I mean, for such mobility. The massive MIMO concept all is built around the vision that antennas should be physically small. Small meaning like patch antennas or dipoles or something like that. So the form factor of a massive MIMO array is a lot smaller than what you might initially think of. For example, at the 2 gigahertz band, if you put the elements with half wavelength spacing, then for a 400 element array would be about the same size as the screen you were looking at here. So the vision for a massive MIMO base station would really be like something that looks like a large flat screen TV. So you have like an array of antennas, and they have all the electronics mounted on the backplane behind. There'd be something like this thick, and that's it. Every antenna has its own RF and baseband processing chain, and the output powers that we're talking about here are quite small per antenna, on the order of 10 or a few tenths of milliwatt. And the reduction of radiated power as compared to conventional wireless is all facilitated by the array gain that massive MIMO offers us. I mean, the fact that these, due to this concentration of power that occurs here, which has the interpretation that we're really focusing power onto particular directions in space. Yeah. All right. So, yeah, okay. I mean, hardware is also fairly mature at these bands here. Phase noise in particular is not really a major problem, which as opposed to sometimes in millimeter wave bands, you have more issues with phase noise. So, question, is reciprocity-based MIMO in TDD the only reasonable way of implementing massive MIMO? Well, that's an issue that's been debated for a long time, and I'm saying here that massive MIMO should be built exploiting reciprocity in TDD. It is also possible to some extent to build FDD flavors of massive MIMO that work, and I think tomorrow is going to be devoted to the details of that approach. One thing that's quite interesting to do is to compare the performance that can be achieved in TDD mode, relying on reciprocity, with a performance that could be achieved using solutions that rely on FDD. And in FDD, we would have the feedback channel responses. I mean, we would have, for one thing, the base station would have to broadcast pilots in the downlink. Every terminal would have to estimate the channel responses and feed them back to the base station on the uplink. So suppose that came at no additional cost. Then would TDD still be better? Well, the answer seems to be yes. I mean, this is from a measurement campaign, a paper that measurements that were done by Lund University in a paper that was done in the Mammoth project that I had the pleasure to collaborate on. What we did here was that we compared, using measured data, the performance of fully digital reciprocity-based MIMO in TDD with FDD grid of beams type of solutions. And this was done for an outdoor scenario. So there was an array mounted on top of a building. It had 128 antennas, and it was done on a 2.6 gigahertz carrier. Okay. So now, as far as FDD or grid of beams based solutions are concerned, there are a couple of different ways that we can implement those. Okay. For one thing, we could, have the terminal. So we'd have like fixed predetermined beams like this. Okay. And but for one thing, we could have every terminal to report one beam index for every subcarrier. Or alternatively, we could have every terminal report one beam index for the entire band. Yeah, so those are like the two rows here. And there are a couple of other different options in terms of the processing that you can do as well. You could either have every terminal send back its own beam indices, or you could have somehow the base station trying to find some set of joint indices that work well for all of them together. It turns out in practice, there are like 4 combinations here. So it turns out in practice, it doesn't make a big difference which of these 4 possible approaches that we take. Grid of beam type approaches are significantly inferior regardless of how we do it. And just to get a glimpse of those results, these are numerical plots that show for 3 different scenarios, okay, 1, 2, and 3. And in the first scenario, there was line of sight to 4 terminals, and they were like spatially well separated, so they were really at different places like this, okay? In the second scenario, there were 4 terminals that were like a meter or so in between, and there was none line of sight to them, okay? And in the third scenario, there were like 4 terminals that were reasonably close, like a meter or so, and there were line of sight to them. So there are like 3 graphs here, okay, 1 for each one. And these graphs here, they show, so the different lines are just the different approaches to how to actually do the grid of beamforming. And these graphs show here how large a fraction of the reciprocity MIMO capacity that a grid of beams-based solution could achieve. So 1 here would be same performance as TDD-based, reciprocity-based MIMO, okay? And N here, that's the number of beam indices that every terminal reports back. So now the important conclusion is really, by glancing at this figure here and see that, well, if you have line of sight, then, some of these techniques can work reasonably well. But if you have non-line of sight, then obviously, if you feed back all the beam indices, then with some of these techniques, then you're going to get the full reciprocity MIMO performance. But even if you have feedback like 10 beam indices per terminal, which is still quite a lot, you're not going to get more like 40% or so. So measurements do suggest that TDD-based, reciprocity-based MIMO is vastly superior to any style FDD or grid of beams-based approach, and that's an important take-home point. Another problem with massive MIMO in FDD mode is that it doesn't scale well. And to understand this, let us contrast the requirements for pilots and for channel feedback in FDD and TDD. So there is something in communication theory that I like to refer to as the half-and-half rule. And it states that in a good system design, you should not spend more than 50% of your resources on pilots. Okay? So let's first look at TDD. Yeah? In TDD, there are only pilots in the uplink, no pilots in the downlink. And there is no feedback of channel state information. Okay? And in TDD, we have 1 coherence block, which is common for the uplink and for the downlink. That coherence block is this many samples long, BC times TC. BC is the channel coherence bandwidth, and TC is the channel coherence time. Okay, so now we are at a few gigahertz carrier. We are outdoors in a suburban environment. We have highway speed mobility. Then BC times TC is in the order of 200. Okay, so we have 200 samples, and we take these 200 samples, divide by 2 because of the half-and-half rule, and we get 100. Okay, and note that it's coherence block. This is the number of, this 100 is the number of samples that we have available that's going to host the pilots, right? And since every terminal needs its own orthogonal pilot sequence, then the number of terminals that we can possibly support will be less than 100. But it's the only requirement that we have. So there's no limit on how many base station antennas that we could usefully deploy. In contrast, in FDD, there will be 2 separate coherence blocks, because those are different carriers, 1 for the uplink and 1 for the downlink. First, in the downlink, we're going to have to send pilots, which are not beamformed, but pilots that are broadcasted omnidirectionally, okay? And the way they have to be implemented is that every antenna at the base station would have to send a pilot sequence, which is mutually orthogonal from the pilot sequences sent by all other base station antennas. So in order to accommodate that orthogonality requirement of the pilot, the number of base station antennas that we could usefully deploy would have to be less than this number of samples that we can play with, which is 100. Okay? In addition to that, we also look at the uplink. Then in the uplink, we would need 2 things. First, the terminals would have to feed back the channel estimate that they learned from the downlink. That's how FDD works, right? So the terminals estimate the responses to all the base station antennas and feeds that back. And that would cost us this many, with straightforward analog modulation, that would cost us as many samples as we have base station antennas. And on top of that, the terminals also would have to send uplink pilots to facilitate the detection of the data in the uplink. So that would cost us as many samples as we have terminals. So, and then we have this number, which is 100 here. So number of antennas plus number of terminals would be less than 100. So we have these inequalities. We can visualize these inequalities. For TDD, we get a rectangle like this. So this is like a feasible operating region, where here we have number of terminals, and here we have number of base station antennas. So for TDD, it will be this rectangle here, okay? There is a limit on how many terminals that we can multiplex. My toy numbers here, that would be 100. But there's no limit on how many antennas that we can usefully deploy, okay? With FDD, in contrast, we get this triangle here. Yeah, we have to pick some operating point inside of the triangle, say here. And that would be like 50 terminals and 50 antennas. And that would be it. So these are really the fundamental reasons for why TDD is definitely always preferable in a practical, I mean in practice. Yeah. Okay, any questions on this? Yes? So there are two distinct effects here, okay? One is that, one is the question on if you wanted to do FDD MIMO and really feed back the complete channel responses, not relying on structure of the propagation environment, okay? Then you would hit this effect here, where there's a firm upper limit on how many antennas that you could usefully deploy and how many terminals that you could ever multiplex to. The other effect is that if you think that you could get away with not feeding back the complete channel response, relying on some kind of perceived structure of the propagation environment, thinking that there'll be beams or something like that, so it would be sufficient to have a predetermined grid of beams and have the terminals feedback indices associated with those beams. Well, that sounds nice in practice. It sounds nice in theory, but it doesn't work well in practice. Once you go out and you measure and you start to look at real channels, you'll discover that in fact there is no such a thing as a grid of beams. I mean, as soon as you have non-line of sight, then anything based on such feedback of beam indices works exceedingly poorly as compared to reciprocity TDD-based massive MIMO. So there are really two distinct effects here at play. Yeah. Yes.
Usually this hybrid beamforming schemes aim the millimeter wave right? So these measurements are for 2.5.
That's correct. This is for low frequencies. Yeah. So I mean, we're going to hear more about, well, I mean, let me say also there are a lot of people that believe that it's kind of hybrid solutions would work at lower frequencies. Well, it seems they don't. Okay. For millimeter wave, might be a different story because you have more of line of sight like propagations. I think we'll see that tomorrow, in fact. But yeah. Yes.
So in this unique assume that the channel is ideal. In reality, you have different orbits down in the node. So if you take that into account, will this change the figure?
So the question is whether, this channel reciprocity that I claimed here holds in practice or not. And clearly, as far as the actual propagation channel is concerned, reciprocity holds. I mean, it's a consequence of Maxwell's equations. Then in practice, you'll have an effect where you have a different electronics chain for the receive path and for the transmit path, and those have to be kind of calibrated relative to each other. So to exploit reciprocity in practice, you need calibration algorithms, and there are such algorithms, and those have all been tested in practice. I mean, and some certain testbed hardware that I'm aware of, then recalibration had to be done like once per hour. Once the equipment had warmed up, you could do it once per hour, and there was still really no need to do it. So it really seems that calibration is a non-issue. I mean, as demonstrated in fact in practice in various tests. And also, if you think of it, I mean, you can in fact live with a pretty large phase error. If you think of forming a beam, right, and you have phase errors on your weights, even you would have a phase error of something like 60 degrees. Cosinus of 60 degrees is what, 1/2, right, or something like that. So, even with 60-degree phase error, which is really a lot, you'd lose like a cosinus of 60, which is 1/2. You'd lose like 3 dB or something of that order, right? So, in practice, you might have like a 1-degree error. So it's really no big deal in practice. I mean, compared to in fact, compared to the channel estimation errors, which occur due to mobility and finite channel coherence, reciprocity imbalance seems to be really an absolutely minor point. Yeah. All right, great. So let's see. Up next. All right, some history of MIMO and massive MIMO. So at first there was the idea of point-to-point MIMO, and the information theory for that was developed in the 90s, about 20 years ago. And in point-to-point MIMO, the idea is that you would have a base station with, an array of antennas, and that base station would be communicating with a terminal that itself had an array of antennas. You'd have like an M antenna base station and a K antenna terminal like this. And one of the things that are known about point-to-point MIMO is that there are neat closed-form expressions for the channel capacity in the uplink and in the downlink. And these expressions take the form of a log determinant like this, where G here is a matrix that comprises these channel responses between every base station antenna and every terminal antenna. And K number of terminals, M is the number of antennas, and rho here is a measure of the signal to noise ratio. So if you do this, in principle, you could communicate at rates given by these formulas here. However, the only way of communicating simultaneously with multiple terminals would be to schedule them on orthogonal resources, which means in practice you would put them on different subcarriers, so you would put them like at different points in time and so forth, okay? I guess the reason that point-to-point MIMO never really became a hit in practice, there were two reasons. One is that it requires the use of multi-antenna terminals, okay, which are complicated in its design. You would need RF chains here to operate independently for all these antennas and so forth. And in practice, there's a limit how close you can put antennas. On any sort of mobile device, So, and the other reason why it's never really took off well is that for this to work, the propagation environment has to support K streams here, which means in practice that this channel matrix G here should have rank equal to K, okay? And that never really happens. If these antennas here are very closely located, then in practice, then this rank is not going to be K. And particularly if you have line of sight to your terminal here, then this channel matrix called G here is going to be rank 1, which means in practice that you cannot multiplex. You can't send more than one stream. Ideally, you would think you could send K streams, because this logarithm here scales with the dimension of G, right? But if you have line of sight and G is rank 1, you can only send one stream. Yeah, so that's point-to-point MIMO. And then came along multi-user MIMO. So with multi-user MIMO, the idea is that you would have your base station with an array of antennas, and these antennas would now be used to multiplex many terminals at the same time, okay? And in its canonical form, these antennas would these terminals would just have a single antenna each. And the information theory for multi-user MIMO is a little more recent. It's like early 2000s. And it's actually more than a little bit more complicated than for point-to-point MIMO. But it is possible to show that there are, to prove formulas for capacity, actually for some capacity, this is sum over the rates of all terminals, some capacity for the uplink and for the downlink. And these formulas here, they look like this. On the uplink, there's a log determinant. On the downlink, there is a log determinant. And then there is some optimization over weights here and so forth. Well, looking at these formulas and comparing them to the corresponding equations for point-to-point, they are deceivingly similar, right? In fact, the formula for uplink capacity in multi-user MIMO here is formally identical to the formula for the uplink capacity in the point-to-point MIMO case. But this is a little dangerous. In fact, it's almost a little paradoxical that it comes out this way, because the operational meaning of these formulas for the multi-user case and the point-to-point case are fundamentally different. The difference lies in the fact that in the point-to-point case, the antennas here at the terminal, they can collaborate in the signal processing, right? You can bring all these signals here into one single, processor and do whatever you want with them, okay? But in the multi-user MIMO case, these terminals here, they are autonomous. There's no way that they can collaborate on the signal processing, which is required either on the uplink or on the downlink. Even so, as it turns out, the actual formula for the SAM capacity on the uplink here is the same in the multi-user MIMO case as in the point-to-point MIMO case, which in itself proves that on the uplink there is nothing to be gained by the ability of the transmitting antennas to collaborate. They might as well just send independent streams and that's it, right? So multi-user MIMO is a lot better than point-to-point MIMO. One reason is that it is a lot less sensitive to propagation. In particular, it works well even if you have line of sight to your terminals here. Even with line of sight, then the rank of this channel matrix G is likely to be quite large. It works. It also works with much simpler terminals, with single antenna terminals, which might be an advantage when you actually start to build this electronics. But it has a significant drawback, and that is that the signal processing required in order to achieve the capacity given by these formulas here is very complicated. Okay? On the uplink, we need something called successive interference cancellation, which is a very sensitive type of signal processing. It's very prone to error propagation and all sorts of problems. And on the downlink, we need something called dirty paper coding, okay, which is like a pretty toxic, information theoretic method that you don't want to deal with, let alone implement. So to achieve these formulas, you need very complicated signal processing. And also importantly, in order to achieve capacity given by these formulas, then everybody in the network needs to know this channel matrix G perfectly, okay, to do this successive interference stuff for this dirty paper coding. Everybody needs to know G perfectly. And as I've already touched upon, in practice, we're always going to be limited by the finite channel coherence and the fact that we have only a millisecond to do business, right, before the channel changes. We have only that millisecond to estimate the channel responses before that information is before those are already outdated. So I also would like to take the opportunity here to say that it's always hard to, and some of this is done before my time. So it's always hard to write history, and I think there are some legitimate claims that multi-user MIMO in fact predated point-to-point MIMO. If you go back, to the 80s, there were these ideas that you could. There's no requirements for high data rates or anything. So cellular service was all about providing the possibility to make voice calls, and there were these ideas that you could spatially multiplex voice calls, which is, I think, an early incarnation of the concepts behind multi-user MIMO. So, however, in terms of the actual development of rigorous information theory, it seems that the point-to-point MIMO formulas came along before the multi-user MIMO formulas came along. Yeah, okay, great. So, any questions? Yes?
So the difference between multi-user MIMO and the single-user uplink, having the same formula, does it mean that even if we have cooperation between the users, it doesn't bring much? It doesn't bring anything much?
That's correct. On the uplink, there is nothing to be gained by the ability of the terminal antennas here to cooperate. That's correct. Then in practice, this is all information theory, which holds, in this case, under the assumption that G is perfectly known everywhere, that the block lengths are infinite, and you can do infinitely complicated signal processing, right? So in practice, there might still be a reason to let them cooperate, but fundamentally, there isn't anything to gain. Great. Any questions? Okay, so how does massive MIMO then come into this scene? Okay, so massive MIMO is, in principle, is an incarnation of multi-user MIMO, massive MIMO takes multi-user MIMO to the ultimately useful operating regime, where we have a large number of antennas at the base station, M, large number meaning like 100 or a couple of hundreds even. We are multiplexing to many terminals simultaneously, and these terminals have single antenna each. Extensions are possible, but I won't talk about them here today. I'm not sure Emil will talk in the afternoon at all about multi, maybe a little bit, yeah. But in the morning, we have single antenna terminals. And we have many of them, tens of them, that we multiplex simultaneously. M is much greater than K. Typically, it doesn't have to be the case, but normally, 100 is much larger than 30 at least. So in that respect, M is much greater than K, yeah. It turns out in this regime, linear signal processing that I spoke a little bit about earlier already is the optimal thing to do. So there isn't anything or really much or marginally much to gain by applying anything more complicated, okay? The base station learns measures the channel on the uplink through pilots. And an important phenomenon enters the scene known as channel hardening. Okay? Channel hardening means the following. Suppose that I am the base station and I'm beamforming to somebody in the downlink. I'm beamforming to the case terminal. Okay? And the case terminal has a channel vector which is GK. So that's a vector with M elements. And I'm applying a beamforming vector to the case terminal which is VK. Okay? So you're the case terminal. And what you're going to see is an effective channel, which is scalar. Yeah? And the gain of that effective channel is going to be the inner product between GK and VK. So that's GK transpose VK like that. Okay? So now, if these vectors here, they have M elements. So this inner product here is like a sum of M random things. Right? And a priori, the case terminal does not know this gain of the equivalent scalar channel. It's unknown, right? It's a priori unknown, and nobody knows it a priori. However, because of the law of large numbers, this inner product here is a sum of M random variables. So that inner product is going to be very close to its statistical expectation. Yeah? So in practice, this effective gain here, that scalar random number, is going to fluctuate just slightly around its expected value. And that expected value, that is a deterministic quantity that is known to everybody, right? So in effect, the case terminal knows, it doesn't know this gain exactly, but it knows it approximately. Okay? And that channel hardening has important consequences. One consequence is that when the K terminal wants to decode, it knows that it sees its data through a scalar channel. Yeah? And that scalar channel has this gain here. And that's a random number, okay? And it's not known a priori. However, we know that it fluctuates only slightly around its statistical mean. The consequence of that is that there's no need to transmit any downlink pilots or downlink reference signals for demodulation. So we can get away with those, do away with those. The second consequence of channel hardening is that all the effects of the small-scale fading will go away. In particular, while this is a random number, okay, which will be different for every subcarrier. Think of an OFDM system. This is going to be different for every subcarrier. However, the statistical expectation here is the same for every subcarrier. Yeah? So what the channel hardening does for is that it effectively removes all the frequency dependence in the system. So you can think of this in the UFDM context. Every subcarrier is equally good. Okay? So there is no point any longer in scheduling terminals in the frequency domain and say that you get this part of the band and you get some other part and so forth. You better give everybody the full bandwidth and multiplex them spatially instead. And that's an important take-home point here. Okay. A third consequence of the channel hardening is that while this effective gain, as I said, it's random, and it will vary a little. I mean, it will vary with frequency, it will vary with time, and so on. that statistical expectation is not. And all the resource allocation that we want to do, resource allocation, think scheduling, think power control, and so forth, that can be based only on that statistical expectation here. Which means that there is no need to do anything frequency adaptive, per subcarrier adaptive, or even time adaptive. Everything can be done on a slow time scale, and power control coefficients in particular are recomputed only when this statistical expectation change. And that statistical expectation in turn will depend only on the path losses and shadow fadings and so forth, which change very slowly in wireless, a lot slower, more slowly than the small scale fading does. So here's an illustration of this channel hardening, because a lot of people have contested. Oh, by the way, here's an illustration of the frequency independent scheduling. So if you think like this is a time frequency grid, right? Grid, like if this were like LTE, then you would schedule, terminals all over the place here. Some terminals would get a small chunk of bandwidth up here, and others would get some small chunk down there, and so forth. And in massive MIMO, in contrast, you just give every terminal the full bandwidth. And if there are latency constraints, they might have to schedule them in time. But that would be it. So now concerning, yes. So the question is, if you do zero forcing, then what G is going to look like here. Yeah, okay, but yeah, okay. With zero forcing, if you had perfect channel knowledge, I mean, it should really be the V here. If you had perfect channel knowledge, then V here would be like the kth column of the pseudo inverse, and then correctly, this whole thing would be equal to 1, right? Now, in practice, when you construct your precoder V, you don't know G perfectly. You only have access to an estimate. So therefore, with zero forcing precoding, you're going to get something here which is equal to 1 plus some kind of estimation noise. Yeah.
And this is why we start talking about channel hardening, because of the fact that we imperfect channel estimation.
Yeah, that's correct. Yeah, right. Oh, that's a good point. Thank you. Yeah. So, all right. So concerning this channel hardening, a lot of people had difficult. I mean, I guess nobody contests the math here, and obviously, I mean, this can, we do this rigorously, right? But just trying to use some intuition for the main effects that are in play here. But a lot of people contest whether channel hardening really exists in reality, and this is an experimental result from the same set of measurements I showed earlier, where I think this is a histogram of received power with a single antenna, and then with maximum ratio processing, the effective channel. You can see here how the distribution of the gain concentrates around its expected value. So channel hardening is a very real phenomenon. It's out there. You go out and measure it and see it, right? So it's not a mathematical artifact. It's something you actually see in practice, and that I think is an important point to bring home. I myself got into this topic back in 2009. In 2009, massive MIMO was still a bit of a crazy topic. People argued that sort of base stations with hundreds of antennas could never be built, be impossible to get the electronics working, reciprocity would not hold, TDD is not going to work, phase noise is going to limit ultimately performance and so forth. I had along the way the opportunity to work with some real hardworking and knowledgeable and talented people. It's a paper we did in 2011, the Ellerton Conference on Energy Spectral Efficiency. The journal paper that we published subsequently won one of the major ComSoc awards. You might think that that paper would be easy to publish and that reviewers would say that this is outstanding work or push it your paper easily through. Turned out, in fact, the opposite. The first version of that paper was almost rejected. We had to fight pretty hard to have it published in the end. So it really seems like paper reviews are really poor predictors of eventual impact of papers. I furthermore had the privilege to work with a team of talented people, not only my own group, but also Chalmers at Bell Labs and also people at Lund University in Sweden who have conducted a lot of experimental and channel modeling work on massive MIMO. This is what the IEEE Signal Processing Magazine editorial staff thought that a massive MIMO antenna would look like in the year of 2012. All right, so by the way, among the authors of the paper here, Daniel, I think, is in the audience, yes, hands up. Okay, great. So we injected, we started this topic, and it was all, a bit of crazy in the first years, and people did not believe it. But as we know, year 2017, massive MIMO is the main work item in the 5G standardization for physical layer. Is evidenced obviously by a fair number of standards contributions that are currently being processed. So it's been a really exciting journey to be on board of this for the last 10 years. And massive MIMO using reciprocity beamforming does work in practice. I had along the way the opportunity and privilege to work with some experimentalists at Lund University in Sweden, and that was all done in the FP7 Mammoth European project, where one of the final outcomes was a field demonstration of massive MIMO multiplexing in real time. And here are some screenshots from that. So there's this testbed that they built on top of the roof. Here is a 3.6 gigahertz piece with 128 antennas, and all multiplexing to, there were terminals down here in the parking lot. There were 12 of them. 4 of them were on cars and 8 of them were on bicycles. So multiplexing to 12 terminals at the same time, and some of these were moving quite fast. I mean, 30 miles an hour, that's like 50 kilometers an hour in a parking lot. I mean, it's pretty much racetrack style driving there. So it all demonstrated with clarity that, all this reciprocity, channel estimation, all that, it works. I also would like you guys to bring back the point that technology does progress. And again, when we started my team with massive MIMO back in 2009, then I would go around and give talks and suggest that we could do zero forcing processing to 10 terminals, and people would say that it's not going to work because you're going to need a supercomputer somewhere at the back of the room to support that. And a few years later on, we made some estimates of power consumption, and we concluded that if you would just take off-the-shelf kind of high-end DSPs and program these to do the job, you would probably need a few tens of watt or something like that. And then last year, my colleagues at Lund, and that was within this Mammoth project, they uncovered a circuit. This is a working prototype, actual silicon circuit that it does this zero forcing precoding for massive MIMO with 128 antennas and 8 terminals simultaneously in real time over a 20 megahertz bandwidth, and that's all done with a power consumption of 50 milliwatt, which is pretty much nothing. I mean, you could do like a handset, 50 milliwatt is nothing, right? So obviously on top of this, there's going to be FFTs and filters and coding and all sorts of processing. So I mean, a lot more, and there's going to be analog stuff, which is still significant. But I think that really the take-home point here is that, in something like 10 years, the kind of common conventional wisdom has really changed from something, being viewed as impossible to something that's actually being done on silicon at no power consumption at all. So I think that's an important thing to remember. Okay, great. So to understand more quantitatively what massive MIMO can do for us, here's a little simulation exercise that teaches us a few useful things. The graph specifically shows the sum spectral efficiency within a single cell that we can achieve as a function of the number of terminals that we multiplex simultaneously, okay? And this is all done for an embedded multiple cell system. So you're somewhere in the home cell, and then you got guys around you like this other cells. Okay, so there's going to be interference with these other cells, and it's all done for a suburban channel outdoors. So we have a millisecond channel coherence. So think of highway speed mobility at 2 gigahertz carrier, pretty much a millisecond. 200 kilohertz coherence bandwidth, we have 100 antenna base station, and there is power control going on here. There is something known as max-min fairness power control taking place, which ensures that everybody in the network gets the same guaranteed quality of service. Okay, no matter the mobility, no matter your cell border or anything, you get this same performance. And there is pilot sequence reuse, and we're going to return to this point a little later. But let me already say now that there are different ways that you could play around with pilots and with data reuse and so forth. And the canonical assumption in massive MIMO is always that you reuse the same resources for your payload data from cell to cell. Okay, so there's no frequency planning in terms of the payload. However, normally one has to employ some sort of frequency planning for the pilot channel, so to reuse the pilots more sparsely. And in this exercise, the pilot reuse was optimized. Okay, so depending on the actual operating point here, the pilot reuse might be every cell, it might be every third cell, or there's an optimization going on. That's by the way the reason why these curves have a jerk there. It's because of this optimization. Okay, so now quantitatively, we're looking at this graph here. We'll see a couple of things that we can learn. Okay, so the first is that we can achieve some spectral efficiency per cell, which is on the order of 30 bits per second in hertz. Yeah, and that spectral efficiency in turn has to be split among those terminals that we multiplex simultaneously. And the optimum number of terminals that we should multiplex simultaneously, that's about 30 or so. Okay, so at the optimum operating point here, we are multiplexing to 30 terminals simultaneously, achieving a total spectral efficiency of 30 bits per second in hertz. That means that every terminal is getting like a bit per second per hertz. Yeah? And now, importantly, by virtue of the maximum fairness power control, every terminal is getting this rate guaranteed. And that's a virtue of massive MIMO. We can actually do this maximum fairness power control, and it works. Concurrently, if you had a 20 megahertz bandwidth, you give everybody the full bandwidth, so everybody will get is 20 megabit per second rate guaranteed, no scheduling, okay? So that we can learn. Another thing we can learn here is that the performance of zero forcing, the maximum ratio processing, is pretty much the same. Yeah? So we spoke before the break about its ability that zero forcing has to play spatial nulls to get rid of interference. It turns out that ability isn't that terribly important in practice. It happens because we have a high mobility environment here, so we got only a millisecond to estimate the channel responses. So we can't really form extremely accurate estimates. So these nulls are going to end up a little bit in the wrong place here and there, and zero forcing gives a little better, I think. Yeah, like, I don't know, 30% maybe, but not really more than that, okay? And so it's because it's difficult to estimate the channels accurately. Another reason, as I think I touched earlier too, is that even multicellular environment, you're going to have interference. I mean, zero forcing can handle interference within your home cell to some extent, but it does nothing to combat interference that comes from other cells around you here. Notwithstanding that, it is possible to do other more sophisticated types of processing that also deals with the out-of-cell interference. I think Emil in the afternoon is going to talk about more advanced topics like that, but I won't touch them here more. Okay. So pretty much the same, performance for both these guys here. So one more thing that we can learn from this graph is we look at the shape of it and we see that it starts at 0, right? Obviously, I mean, if you don't have any user, then you're going to get a rate. But anyway, it will eventually return to 0. So why does that happen? Well, that happens for the zero forcing processing because if you try to multiplex 100 users and you have 100 antennas, then you're going to exhaust all your spatial degrees of freedom when you place these nulls. So there's no way you could accommodate more than 100, okay? So it just breaks down there. But in fact, if you look at the curve for the maximum ratio, you'll see that it slowly tends down to 0 as well. And if you were to continue this curve down here, it would also hit 0. And it would hit 0 at the point where we multiplex 200 users. So why does that happen? Well, it happens because of the finite channel coherence. Remember, this is high mobility. We have millisecond by 200 kilohertz. If you multiply these two numbers, then you get the number of samples that every coherence block has to offer. 1 millisecond by 200 kilohertz, that's equal to 200. So we have 200 samples per coherence block. If we tried to multiplex 200 users, then we would have to spend, in order to give these guys orthogonal pilot sequences, we would have to spend all these 200 samples on pilots, right? And there will be no time left for any data transmission. So that's why the blue curve eventually also goes down to 0. So that's another important thing that we should learn from this graph. Yeah. Okay, great. Any questions on this? Yes. Yeah, so why there's a jerk here? That happens because the optimal pilot reuse pattern changes here. Yeah, once you have squeeze in more and more terminals, then you have to use a denser pilot reuse pattern. Otherwise, you cannot afford the training overhead. So that's why that happens. If you have only reused one, yeah, okay. For this one, I mean, they're gonna turn down quicker. But I have a couple of case studies that'll come later on that I think will address this point with different reuse factors. So just think of this as a way of learning, you know, this basic phenomena where what happens when, you know, you increase K and so forth, the number of users, yeah, zero forcing versus maximum ratio.
Is this based on a perfect channel estimate?
No, this is not based on, so that's the point. This is the important, you know, question. This is all assuming that channels are estimated independently in every coherence block.
How is the channel estimation error model in this scenario? How do we model? I mean, what is the delta between this and having a perfect channel estimate?
Right. Okay. So the question is how the channel estimation is modeled here. So channel estimation is done based on the received uplink pilots using an estimation technique known as MMSE estimation. I think I have a couple of slides a bit later on. We get a little more into mathematical, you know, aspects. For now, just think of it as kind of the best channel estimation you can do in this context, right? Yes. This is all independent Rayleigh fading. Yeah.
So, for example, if it was recent, it could be like the zero forcing is much better than.
Well, possibly in some environments you could, you know, see that zero forcing offers a little more. But in fact, and I'll be returning to this point, the choice of channel model does not make a huge difference for the eventual performance that massive MIMO can offer you. And if you can live with that, I'll park that question until we get to that part here. So I think it's very important. Yeah. Yeah. Okay. Great. Yeah. Yes. Could you please repeat that? Well, I mean, with zero forcing, you cannot do it. Huh? With maximum ratio, there is no limit on how many terminals you could multiplex. However, as you see, you look at the maximum ratio curve, it's pretty flat here, right? And eventually it will go to 0 because the training cost. But even at this point here, you would have like 100 users and 25 bits per second in total. So every user would get like 0.25 bits per second per hertz. So what happens is with maximum ratio, you add more and more users and multiplex them. You can do it. But the effect is that the total spectral efficiency doesn't increase anymore. And everybody just gets less and less rate. You get more and more terminals, but everyone gets less and less rate each one. Yeah. So, okay. Yeah. Great. Okay. So here's another illustration that brings home the point that downlink pilots are not needed in massive MIMO. And I think I touched this point earlier when we spoke about this channel hardening phenomena. These figures just quantify, those claims. So, in fact, here we're looking at two different fading models. On one hand, we have independent Rayleigh fading, which is like the canonical model for massive MIMO, and it's a canonical model. It's very useful because it turns out to be very analytically tractable and leads to very nice, expressions and formulas. On the other hand, we have a model known as the keyhole channel. A keyhole channel is a channel where there might be some scattering going on, but any wavefront which is observed by the base station array has passed through a small number of narrow slots. Okay, and in a way, keyhole channel is the worst channel that you can think of. I know some people who tried to find a keyhole channel in measurements and they didn't succeed, so they ended up having to build one, actually taking a sheet of metal and slice it to observe the effect. So you think of keyhole channel as really the worst that you could ever be exposed to, right? And it might not exist even in reality. But the point here is that in the independent Rayleigh, the channel hardening effect exists that we spoke of earlier, the fact that this effective gain is close to its deterministic constant, okay? In the keyhole channel, the channel hardening effect does not exist. So we would think that if we had a keyhole channel, then having the terminals rely on the belief that their effective gain is approximately equal to its statistical mean, that would give very bad performance, and maybe some downlink pilots could help in that case. So quantitatively, how this plays out is as follows. This is a simulation example, 100 antennas, 20 terminals, some SNRs. This is a spectral efficiency on the vertical here. Length of the coherence interval in samples on the horizontal. And you want some numbers, then suburban, outdoors, high mobility. It's good to remember that's about 200. Okay? So now in the independent relay case, spectral efficiency, there are three curves here. There is the black with the dots. That is relying on hardening, okay? Relying on what I spoke of earlier, that the inner product between this channel response and the beamforming vector is approximately equal to its statistical mean. And then the red curve is that's when we send downlink pilots, okay? And that's a lot worse. And the reason it's worse is that these downlink pilots, while they do help the terminal in its decoding, they will cost resources. Every coherence block, we have to set aside 20 samples only for the sake of transmitting those downlink pilots. And the cost of doing that is reflected in the gap here. And we also, some years ago, developed an algorithm that could, not relying on hardening, but that could estimate this gain. I think we had it earlier here somewhere. What was that? This gain here. Estimating this gain blindly, okay? So instead of telling the terminal that please assume that it's equal to its statistical expectation, or instead of relying on the transmission of a downlink pilot that would facilitate the estimation of this gain, we had an algorithm that the terminal could just look at its received samples and solve some equations and get an estimate of how large that gain is. And in the graph here, you can see how well that performed. So in the independent relay, it was as good as relying on the hardening. So clearly in the independent relay case, there is no point sending the downlink pilots. Now, question, how about in the case with the keyhole channel? It turns out in the keyhole channel, the picture is a little different because hardening doesn't hold. So if we tried rely on a hardening effect, then we have very poor performance. It's a black here, okay? Yeah. Sending downlink pilots is certainly beneficial. Since we can't rely on hardening, we need some other mechanism by which the terminals can estimate their effective channel coefficient. And sending a downlink pilot is a good way of doing that. But in fact, with a simple blind algorithm, you can do even better than with the downlink pilots. So that's an important take-home point here, that downlink pilots are not needed. That's one thing. Another thing is that if we have an environment where hardening holds, well, then we can just rely on that hardening and we'll be fine. Were we in an environment where hardening would not hold, well, then we would need some kind of clever algorithm or possibly, rely on the transmission of some pilot in the downlink anyway. Yeah. Okay, great. Any questions on this? Yes.
The decoding vector we use for the downlink. Do we do the decoding based on the estimates for uplink? Our uplink estimates in the base station, or do we do it randomly? Without anything?
That's correct. So all the beamforming in the downlink uses the channel estimates learned on the uplink. Correct.
So this is for TDD, mainly for TDD.
It's all TDD. Everything here is TDD. Okay. So I won't talk about FDD at all. I mentioned it in the morning. I'm not going to talk more about that. I think also Emil's lecture in the afternoon is going to be all TDD. Tomorrow we're going to hear about FDD, massive MIMO. For now, just forget FDD and think TDD. Yeah. Okay. Yeah. All right. Great. So I will next be returning to the question that someone asked just a minute ago. Yes, you have. Yeah, okay, so the question here is whether in order to, I guess you're referring to the blind algorithm, how much of side information that needs to work. And the answer is, this is all, under that block fading information theoretic model. where anything that's random is a priori unknown to everybody, and anything that's deterministic is perfectly known to everybody, right? So here, I mean, all the path losses and all those would be like deterministic quantities, so everybody would know them. In practice, you would need some kind of mechanism to furnish knowledge of those parameters to the terminals. So it's in that way a little bit idealistic, but the point is that there's no need here for any, I mean, any transmission of any, say, information that change frequently, right? Yes?
How users do data demodulation? This means that they even don't need phase of channels?
That's correct. So the question is whether how the terminals can demodulate, whether they need any phase information or something. It's a good question. I mean, so in fact, you know, if we return to the basic formulas that we had, I think, up here, then this is the gain of the effective scalar channel that every terminal sees, right? And I said earlier, this is approximately equal to its statistical expectation. It turns out that for the precoders they were interested in, this here is a real valued number, so the phase is 0. At any rate, no matter what the phase would be, this is deterministic, right? It's the expectation of some random numbers. It's deterministic. So, you know, it'd be a value that the terminal knows, right? So you could just rotate the phase, right? So you would not need a phase. You would not need a downlink pilot to get the phase right. That's correct. Yeah, it might be counterintuitive. Actually, a lot of stuff in massive MIMO is counterintuitive the first time you encounter it. Even the fact that, you know, I mean, in the early days of massive MIMO, there was this belief that when you add more and more antennas, then obviously you get more and more channel responses, which are a priori unknown, and therefore need to be estimated. So when you add more and more antennas, you get more and more unknowns in the system, right? So that sounds like it should be a problem. I mean, performance should decrease when you add more and more unknowns. But the paradox of massive MIMO is that, notwithstanding the fact you get more and more unknowns, you still get better and better performance. So there are quite a few things here that might at first sight appear counterintuitive, but once you work out the math, you'll see that they fall in place. Say again, please.
Is it some sort of statistical CSI? Statistical CSI?
Yeah. Okay. So a lot of people like to refer to. I mean, to the fact that, you know, knowledge of deterministic quantities is called statistical CSI. I just here, let's simplify. Think of them as. I mean, think of this in a way that everything that's deterministic, okay, is known to everybody. All deterministic quantities are known to everybody. And all statistics are deterministic. I mean, if you have a random number, you take the expectation, you get something deterministic. So therefore known to everybody. Some people refer to that as knowledge of statistical channel state information. Yeah.
And how does the recursive algorithm, because the variation is very low, so how does the recursive algorithm perform over there? Such as recursive B-square or
Wow. So the question is whether a recursive algorithm, how that would perform here.
better than others?
Well, better than, so just making sure I get the question right. I mean, but maybe I should underline the fact that everything I say here is you know, based on this block fading information theoretic model, right? Where channel is static over one coherence block, and then it changes independently to the next. And under that model, there is no point in doing anything recursively. You just do your business within every coherence block separately, and that's it. In practice, you're going to see some continuous variation like this between the blocks. And then, you know, Kalman filtering or recursive algorithms could be beneficial to use in an actual implementation. So the advantage with the block fading model here is that it gives you a nice understanding for performance and for what massive MIMO can do for us. And it also gives us very useful formulas that we can apply for power control, for example. Okay, great. All right, so I'd like to return to a question that was asked earlier, namely, and that concerned the relative performance of massive MIMO in different propagation environments. So to understand this, I'd like us to contrast two environments. On one hand, independent Rayleigh fading or isotropic scattering, and on the other hand, an environment where we have line of sight. So in the independent Rayleigh, or I mean in the isotropic scattering, then we think of the world as being, you know, embedded in an infinite number of scattering objects. And we have an array, a linear array with lambda half spacing. And there's a basic result in wave propagation that states that if you have a stationary random Gaussian field that satisfies the wave equation, then its autocorrelation function is going to be a sinc like this, sinc 2 pi x over lambda. Okay? So if you take that sinc and you sample it at half wavelengths, then you'll sample right at the spot where the sinc has its zero crossing, so you get zero correlation. And that's what underpins the IID Rayleigh fading model. In contrast, in the line of sight model, we instead have we have free space, and we have an array with lambda half spacing. Okay, and then we throw out terminals at random like this, at random angles. And every terminal is going to get a channel response, which is something like a van der Monde vector like this. Okay. So which one of these environments do you think is the best for multi-user MIMO or massive MIMO to operate in? And it turns out that the answer is that they are about equally good. Okay. So here's an illustration of that. This is for the uplink system with 100 antennas and 10 terminals, lambda half linear array. And this figure here, it shows the cumulative distribution, so of the sum spectral efficiency in the cell. And I think the red, so let's see, the blue curve here is for the independent Rayleigh, and the red curve is for the line of sight. Okay. So what might be of interest to look at here is the, say, 99% likely value. That would be where the CDF here hits at 1%. So at that point, the independent Rayleigh, well, it is better than the line of sight, but not really much. Okay, and there's like a gap of 20% or something like that. So from this exercise, we can learn that these environments here, which is fundamentally different, right? I mean, line of sight on one hand is extremely different from isotropic ridge scattering. But in the very end of the day, they offer about the same some capacities. They're about equally good for the operation of a massive MIMO base station. So now think of it, in reality, when you go out and measure, you're very likely to not to have perfect line of sight and not to have perfectly isotropic scattering. You're likely to be somewhere in between of these two extremes, right? So now if massive MIMO works so great, both in the line of sight case and in the isotropic scattering case, well, it'd be very likely that it would also work extremely well anywhere in between of this. And that's also been confirmed. I think Emily in the afternoon's lecture is going to talk about the more sophisticated fading model known as correlated Rayleigh or one ring or exponential ring model and so forth. And you know, you're going to see that you pretty much get the same performance predictions as you get when you look at line of sight or you get when you look at independent Rayleigh. A complication, of course, is the math is going to be a lot more difficult, but it's all there. So that's the important take-home point here, that these environments are about equally good. So to gain some additional understanding for what's going on here, we can conduct a little thought experiment. So suppose that we take these 10 terminals, okay, the solid lines here, and they all start simultaneously. Suppose we take these, and then we take out the two worst of them. Okay, the two, say, troublemakers among them, and we disconnect those two terminals from service in a given coherence block. So we'll be left by serving only 8. Yeah. Then we'll be getting the dashed lines here. Again, the red for the line of sight and the blue for the Rayleigh. And now, when we serve only 8 out of 10, only the 8 best out of the 10, then we get, obviously we lose a little bit in some rate, but line of sight and independent Rayleigh are almost exactly on top of each other. So what really happens here is that, you know, in the line of sight case, right, and we throw out terminals at random like this, different angles, then with some probability, some pair of terminals are going to be very close to each other, almost the same angle of arrival, yeah, and that's what's going to screw up the condition number of the channel. So when we do this terminal dropping here, we go from 8 down to 10. And what we do effectively is that we look through the terminals that we have thrown out at random like this. Is there any pair of terminals that are very close to each other? Yeah? And if there is, then we remove that one. We remove another one. And we're left with 8. And those 8, with very high probability, very well separated. So that's why, you know, we have pretty much the same value as we get for the independent Rayleigh. Yes, there's a question, somebody.
Yeah, you just answered.
Okay, I just answered. Okay, thank you. Yeah. Great. All right. So this is an important, yes.
But I think it also depends on the number of users. So the number of users goes, yes, the result will be different.
So the question is whether if we grow the number of users, the results will be different. And that is correct. I mean, I don't think I had any numerical result with me, but you know, this gap here is going to increase when you add more and more terminals, for the reason that in the line of sight case, the probability that two terminals, two users end up nearly the same direction, that probability grows the more of them you add in, right? So that definitely agree, yeah.
I have a question about this also. For me, I think the initial feeling is that line of sight is very good because you do spread interference a lot. So what happens in this relay fading or ring scattering? You get a problem with interference when you have more users.
So the question is whether isotropic or independent relay would be troublesome in terms of the generation of interference. Yes, of course it will. I mean, if you have independent relay fading, then interference is going to end up all over the place. And that interference we have to deal with. And massive MIMO does that through the coherent processing that goes on in the beamforming. And we're going to see shortly, we get more quantitative how that can play out here. Yeah.
Question.
Yes.
So what you say is basically that in the case with scattering, you randomize the channels, so the probability that two user channels are exactly equal is very low.
Yeah, you can think of it that way. You can think of it that way. Yeah. All right, great. So yes.
What kind of processing is used for these results?
Oh, this was a capacity. This was a capacity plot. So this is the the log depth formula that we have for multi-user MIMO. Yeah. Yes. All right. Great. So okay. The next take-home point here concerns the optimality of linear signal processing. I claimed this already earlier, and this is an example that is aimed at quantitatively showing while the fact that linear processing is so good. So here we have, in this example, we have some spectral efficiency in a cell as a function of the number of antennas at the base station. And this is for downlink, the 16 terminals, independent relay fading. And this is the only plot that I have in the entire tutorial where we have perfect channel state information. And the reason for that is that I would like to compare with known information theoretic bounds, and known information theoretic formulas for capacity. And those formulas are only known for the case of perfect channel state information. So that's only why I have, on this very only slide I have that assumption. So here's now the black line, that's the sum capacity for the downlink. And the only way of achieving that sum capacity is through the use of dirty paper coding. It's a very complicated signal processing algorithm. And then we have the red curve, that is for maximum ratio, processing linear. It actually continued back, it just arbitrarily cut it here to plot looks a bit cleaner. And the blue curve is for zero forcing. So I think the take-home point here is really that if you look at any point in this graph, up here, say 70 antennas serving 16 terminals, then there is a gap. I mean, you could do better by the application of dirty paper coding, but not really much better. You could do like 10 or possibly 20% better, but that would be it. An alternative way of interpreting this plot is to look, at the same point here, maybe 70 antennas, and you get something like 30 bits per second in hertz. Now, if we, instead of zero forcing, did optimal dirty paper coding, how many fewer antennas could we get away with? Well, that would be like looking at this point here, and then move to the left a little bit, right? So instead of, it's hard to see, I can't really, but instead of having 70 antennas, you could get away with maybe 60. All right, so 70 antennas zero forcing or 60 antennas dirty paper coding, you make the choice. So I think that's really like the take-home point here, that linear processing comes extremely close to the optimum. And I should also highlight the fact that, I spoke about maximum ratio, I spoke about zero forcing. There are other linear precoding techniques as well. There is something known as regularized zero forcing. And that turns out to be slightly better than maximum ratio. slightly better than the zero forcing, but it's not really more complicated to implement. So I think in practice that's what you would like to go with. But these are just so nice to talk about and so nice when you play around with performance analysis. We'll stick to those here in this lecture. All right, great. Okay, so I'm a little behind schedule, but I think that's okay. And I'm really happy for the interaction and all the questions that you guys are asking. So just keep on doing that, okay? See how much I can do until 1 o'clock here. So I think, this is like the intro part that we conclude here. Massive MIMO in its canonical cellular form brings us a wide range of benefits. Array gain that translates into improved coverage, scalability with respect to number of antennas, high multiplexing gains, and channel hardening, which significantly takes away all the small-scale fading so that we can, simplify power control and downlink demodulation and all that. And I would like to spend the remaining hour on a little more detailed material. Specifically, we're going to talk about performance analysis. We're going to talk about and touch upon power control, and we're going to see a few more examples from case studies. So I might be going a little faster. It's going to be a little more mathematical, piecewise at least. So I hope you guys can live with that. And as usual, any questions, then please interrupt and ask. All right, so massive MIMO performance analysis. So in performance analysis, one important assumption, and I might have said this already, but one important assumption is that channels, so GK here is the channel response between the kth terminal and the base station array. So it's like an M vector. M is the number of antennas, okay? Channels can be decomposed into a large-scale fading component and a small-scale fading component. Yeah, the large-scale fading component, this is the root of beta k. Beta k is the path loss, which includes also shadow fading, okay? And HK here is like if there's Rayleigh fading, then HK will capture that. So it is important to understand that in performance analysis, the assumption is that nobody knows this channel response a priori, okay? In particular, nobody knows this HK here. It's random, therefore it's unknown, okay? However, everybody knows this beta case. Those are deterministic. Those are what some people like to call statistical channel state information. These path losses are known, okay? So one of the main accomplishments in the massive MIMO over the last 5 years is the establishment of closed form expressions for performance. And I'm going to talk about these expressions a bit. And we'll start by single cell. So in a single cell, there's no multi-cell interference, okay? So we have our home cell and that's it. The home cell has an M antenna array, K terminals, the channel model I spoke of, and I'm going to talk about independent Rayleigh fading now only, okay? I think Emily in the afternoon is going to talk about some other models, but we stick with independent Rayleigh. And we have powers or SNRs, rho in the U in the uplink, D in the downlink. We have power control coefficients, okay? In the uplink, these power control coefficients, I call them eta k here, those are constrained, they are less than 1. They're independently constrained for every terminal, yeah? And in the downlink, we have power control coefficients, and those are, the sum of them is constrained to 1. Because in the downlink, the base station can borrow power from one terminal and spend it on someone else, yeah? So the important thing here is that capacity per terminal can be lower bounded by a formula that looks like this. Okay, it's log 2 of 1 plus something, which is called the effective signal to interference and noise ratio for the case terminal. And then in front of the log, there is a factor here, which some people like to call it pre-log factor because it comes before the log. Okay, and that factor reflects how large fraction of every coherence block is spent on useful activities. Okay, and that's going to be 1 minus the part which is spent on pilot activities. Like pilots are obviously useful, but I should say payload activities, okay? So 1 minus the fraction which is spent on pilot activities. And that's the number of pilot symbols that we send over the duration of the channel coherence block, yeah? And Now, importantly, this effective SINR here, that is available in closed form, which means that there are plug-and-play type of formulas in this table here, okay? And these formulas are all rigorous, okay? So there is no approximations involved in deriving these formulas. And this is an important point, and I'd like to reiterate this, because time to time you hear that people like to do asymptotic analysis, they like to do deterministic equivalence, they like to apply random matrix theoretic approximations and so forth. And that's all nice, I mean, it's all nice mathematics, but it's not needed in order to get these performance expressions. And that's an important point to bring home. There is no approximation involved, there is no asymptotics involved here. In fact, when the massive MIMO concept first came along 10 years ago, then some papers promoted the use of asymptotics and said, you know, let the number of antennas go to infinity and see what happens, right? There is nothing like that involved here whatsoever. All these expressions that I show here are rigorously correct for any number of antennas, no matter how small, okay? Any number m, any number of terminals k. One little caveat is that if m is very little, like, you know, 1 or 2 or something, okay? Then all this is still true here, still valid, yeah? However, these are lower bounds on capacity, which means the capacity is at least as large as this number. And if m and k are very small, then these bounds might be rather loose, not very useful, that means, okay? But as soon as m is like 10 or 20 or something, these bounds are pretty good. So that's the important thing to take home from here. I'd also like to underline, I mean, so you know, I mean, these formulas here, they actually in retrospect look almost embarrassingly simple. I mean, this is all closed form. These are just like rational functions, I mean, to play around with. So why couldn't we do this then for conventional, you know, LTE system analysis, for example? Well, the problem is that we can still do the math, obviously, but again, these bounds here are not going to be very useful or very tight unless m number of antennas is at least 10 or maybe 20 or something. Then so these formulas really become of any value, okay? So now, let us look at these expressions, okay? We're going to look at the uplink with the maximum ratio. So there's this formula here, okay? So we have a rational, like a function, okay? So what's that? Numerator and denominator. In the numerator, we have m, okay? Number of antennas. That reflects the fact that with m antennas, we're collecting m times more power, yeah? Think of that as array gain. Some people call it array gain. And then we have the SNR, not surprising. We have gamma k. Gamma k is a measure of the quality of the channel estimate. Actually, I don't think it's written on the slides, but all of this is all in our textbook, of course, Fundamentals of Massive MIMO. And you know, that's really the place to go when you want to learn this material. And particularly this gamma k is so important that I'd like to write it up, and I really want to make sure I get it right. So I'll cheat a bit and look into the book. This is called, it's called Ultra Reliable Wireless Communications. So you got the gamma k, and that's the mean square value of the channel estimate, so g hat km square, okay? The estimate of the coefficient between the kth terminal and the mth antenna. And this turns out to be something like tau p, that's duration of pilot sequence, rho u, that's the uplink SNR, beta k square, that's the path loss for the kth terminal, over 1 plus tau p rho ul beta k, okay? So you can see here when the path loss is, I mean, when the beta here is very large, yeah. So the SNR is large, the beta is large, then this is going to dominate over that, and this gamma k is going to be pretty much equal to beta k. And then as we decrease the SNR, it's a lower SNR, and eventually this gamma k is going to go down through 0. Okay, so you can never exceed beta k, but it can get mostly beta k if you have really good uplink pilot quality. So all these formulas here, and this is important, okay? They quantify, how to say, they contain the effects of inaccurate. I mean, the effects of imperfections in the channel estimates. So returning, so in the numerator we have this gamma k here, okay, which is for good pilot quality, that's pretty much equal to the beta k, the path loss, okay, and we have eta k, which is the power control coefficient. So think of the numerator, that's the useful stuff that goes in here, okay, and then in the denominator we have that one here that comes from the thermal noise, yeah. And then we have a sum over all terminals, k prime. And we have power control coefficient for the k prime terminal and the path loss for the k prime terminal, okay? And that goes in this part here. This is all intracell interference, yeah? So a question at this point might be, okay, so why in this denominator do you have the sum over all terminals? Shouldn't you exclude the kth one? And just look at the all but kth one that interfere you, yeah? Yes, correct. However, there is an additional effect here, namely that when the terminals demodulate, they rely on this channel hardening effect. Okay, they rely on the belief that their effective scalar gain is approximately or is equal to its statistical expectation. That's not going to hold exactly in practice. So that's going to give a little bit of self-interference. The self-interference people like to refer to as I think we call it gain uncertainty noise. Okay, and gain uncertainty noise also comes in here as additional trouble into the denominator. That's the reason why we have the sum over all the terminals. Okay, so in summary, good stuff divided by bad stuff. So for zero forcing, it's almost the same formula. The difference is that instead of m, we have m minus k. The reason is that when we do this nulling, then we have to spend k degrees of freedom, and that's going to cost us a little bit of array gain. We have less interference. In fact, instead of the beta k, we have beta k minus gamma k here. And remember I said that if uplink pilots are really good, high quality, then gamma k is approximately equal to beta k, so this is small here. So zero forcing is going to do a lot better, okay? But if uplink piloting quality is bad, then gamma k is small, and then the denominator here for zero forcing is pretty much the same as for the maximum ratio, okay? Similarly in the downlink, in fact the only difference is that we have downlink SNR rho d instead of rho u, and we have, you know, the beta k comes outside of the sum here. So these formulas are really clean and simple, and you know, really useful. Not only you can interpret them intuitively, but they're also really easy to hack into MATLAB if you want to get a, you know, simulate the performance of massive MIMO. Really, for a single cell, all you need to do is to decide on the power control policies. How do you select your eta case here, and you can hack this formula into these formulas into your MATLAB code, and you can get some graphs out. So that's really all it takes. All right. Yeah. Okay. Great. I don't know how much of this we'll actually be able to do, but you know, a little bit of performance analysis. Yeah. So this, yes, question.
SNR and the path loss and the shadowing parameters. How are they related? The uplink and downlink rho u and rho d. Are they related to just to the power with which we send compared to the power of the noise?
Yes. Okay. Good question. Correct. So the question is how does rho u and rho d are defined here, and the answer is that they are depend only on the total radiated power relative to the noise. To be exact, in the uplink, rho u is the SNR that you would observe at any one of the base station antennas. If a terminal transmits with its allocated power and your beta is equal to 1. And in the downlink, the rho d is the SNR that you would see at the terminal.
It's not
Yeah.
really the SNR we see in the end.
No, it's not. It's a kind of, I mean, it's a sort of normalized SNR, yeah. So the, you know, so that you normalize the SNR, essentially you can write everywhere that the noise is variance 1, and it cuts back a bit of notation, so it's, you know.
And then the power control coefficients are the ones related to the beta.
That's correct. The power control coefficients eta here, those are, I mean, selected once for all, okay? Recomputed only when the path losses and the shadowing change. So in practice, it means that they will be functions of the betas here. I think an important point I'd like to make already here is that these power control coefficients, when you know, or really power control in general, you look at this, you look at these SINR formulas here. You see, these are rational functions of the power control coefficients. So that means in particular that if you write up constraints, something along the line that you want this effective SINR to be greater than XdB, okay? That constraint will be a linear constraint in these coefficients, which means in particular that a lot of power control algorithms can be implemented through the solution of linear programs. And that stands in pretty sharp contrast to, say, the conventional MIMO or the LTE world, where the idea is that you will have to adapt your instantaneous power along the way, right, from one subcarrier to the next. Here you don't. Here you allocate power only based on the long-term statistics, which is captured in the beta case. And a lot of the power control business can be carried out through the solution of linear programs.
How do you maintain the SNR and independently? I mean, let's say you want to have an SNR of 0 dB.
Mm-hmm.
How can you maintain it in real life without taking into account the beta? I mean,
no, you can't. I mean, in order to do any sort of meaningful power control, you will need to know the betas. Yeah.
I'm talking about the power control. So long term, we do power control long term based on the betas. And we have our instantaneous SNR of 0 dB. So
no, there's no such a thing as instantaneous SNR here. SNR is a long-term quantity as well. Huh? SNR is the expected power over expected noise. Yeah. So maybe I didn't get the question. Maybe repeat one more time.
So basically, the OU and the OD are the SNR, uplink and downlink SNR.
That's correct, and these are fixed. Independently of power control, these are fixed. Huh?
They are fixed for the long fading block.
No, they are fixed forever. Those are deterministic constants. Yeah, that's important, okay? The rho D, this is like, think of the power, you know, rho U is the power. You have a terminal, it emits 200 milliwatts. And you have a base station array, you have some noise figures and some temperature and stuff, okay? That's going to give you a value of your rho U here. Yeah, so that's what it means. So there's no such a thing as instantaneous, you know, SNR, yeah, power here. Great, any more questions on this? This is important, so please ask questions. I'm running late, so I'm going to skip some stuff, but I think it's more important to answer the questions. Yes? Yeah, that's a great question, I mean, and that's in fact the point, that all these expressions here account inherently for the channel estimation errors. And that's what comes in. That's the reason why, among others, you know, in the numerator here, there is gamma k instead of beta k. Yeah, you see that, so the less quality, the lower quality you have on your channel estimates, the less is this value going to be here. Eventually, poor pilot's going to be 0. Yeah. Of course, I mean, in practice, you're going to be limited a lot by with the quality of your channel estimates. Yeah, yeah, we will. Okay, so yeah, more questions? Yeah, okay, not. All right, so I think I had a couple of slides here on some information theoretic analysis, but I think it might be wise to not do those slides right now. We will have time at the end. I'll return to them. Okay, so I'll skip over a little bit, and we'll see. Okay, what comes next? Yeah, we might return to this, as I said. I'd like to amplify the point here because I got some questions also in the break that I said we had this pre-log thing with that goes in front of the log here, and the meaning of that, physical meaning of that. And again, the meaning is that every coherence block we spend this many samples on pilots and this many samples we have in total. So this is what remains for useful activities, right? So the question is now that tau c here, the number of samples that we have available per coherence block, how does that relate to the physical parameters of the channel? And a good way of thinking of that is the sampling theorem. I mean, we have the time frequency domain like this, and we have some chunk the coherence block. And it's so if you have any chunk in the time frequency domain that's t seconds long and b hertz wide, by the sampling theorem, the number of samples that you need in order to represent any waveform that lives in this chunk is going to be b times t. Yeah, so that's really the physical basis, sampling theorem basis. And then, in order to put some some useful numbers on t and b here in channel coherence context, a good way of doing that is. I'll get back to this one. A good way of doing that is to look at a two-path model. And obviously, reality is not a two-path model. Okay, reality has like infinite number of paths, right? But a good way of understanding what's going on is a two-path model. Actually, I think it's like in a worst case. So you have a transmitter, and you have a direct path, and you have a reflected path. Okay, and if the receiver moves a little bit, the channel is going to change. Yeah, so. If you transmit something which is very narrow band, then you're going to receive something which is also narrow band, which is modulated by a factor like this, where if you start with, say, a constructive interference where you stand nominally, okay, so these two paths interfere constructively, and then you move d meters, then they're going to interfere destructively, and then soon again they're going to interfere constructively. Yeah? So you're going to get like a multiplicative factor, like a cosinus like this here. And that in turn is important because if you look at a cosinus here, its magnitude is going to look something like this. Huh? So you can take the channel coherence time to be the time it takes to move from one dip to the next. Yeah, and the distance you have to move turns out to be half a wavelength. Okay, so the channel coherence time in the two-path model will be the time it takes to move half a wavelength. Yeah, and similarly for the coherence bandwidth, what you have to do is to look at if you transmit some sinusoid with a frequency f, complex baseband, you're going to see the channel frequency response is going to look like this. It's going to be a cosinus that depends on the frequency of the sinusoid you send and on the difference in the path length between the direct path and the reflected path divided by speed of light like that. Okay. And if you plot that cosinus, you're going to see another thing that has dips like this. Yeah? And the distance between two consecutive dips is going to be speed of light divided by the difference between the direct path and the reflected path. Yeah? So we take the coherence bandwidth to be the frequency separation between two consecutive dips like this. So that depends not on the wavelength, but it depends on the difference in propagation path lengths like that. Yeah. So coherence time depends on wavelength and velocity. Coherence bandwidth depends only on the difference between the length of the propagation paths. So you take this coherence time, you multiply by the coherence bandwidth, and we get the number of samples that we have per coherence block. And here are some numbers. I mean, one important point is that the number of samples per coherence block varies a lot depending on where you go, right? If you go like pedestrian speed indoors, then you have coherence blocks. You might have 50 millisecond time and 10 megahertz wide, so you have hundreds of thousands of samples. So you could pretty much afford as many pilots as you want in the uplink. There's no practical limit. But if you go outdoors, you might have propagation path length of a kilometer or so, and at highway speed mobility, you'll get down to in the order of hundreds of samples only. And then, channel coherence starts to become a limiting factor. It limits how many pilots you can effectively put into your interval, and the more you put it, it's gonna hit on this pre-log factor that multiplies the log of the SINR. I hope that answered the question, because several questions about this earlier, so also in the break. So, yeah. Okay, great. Yeah, I think this makes that point again. I mean, the net capacity is going to be a penalty factor like this multiplied by the instantaneous capacity. So the longer channel coherence that we have, the more room we have for pilots, yeah, and in turn, the more terminals we can squeeze in and multiplex in the same block. Here's a further illustration of that. So this graph here shows the maximum sum rate that we can achieve, still in a single cell now, okay, for different numbers of antennas and for different channel coherence. And the maximum is obtained by taking these capacities, okay, and summing them up over all terminals. That's what's called sum capacity. And then multiplying by this pre-log penalty that penalizes us because we're spending some samples every coherent block on pilot activities, yeah. And then dividing by 2 because in practice we have to split our resource between uplink and downlink. So it's a bit arbitrary, but dividing by 2, okay? And then we can take this formula, we can maximize this with respect to how many terminals do we multiplex and how many pilots samples do we expend. And the number of pilots do we expand has to be at least as large as the number of terminals that we multiplex. Why? Because every terminal has to get its own orthogonal sequence. Yeah? And that gives us this plot here. Think this is like level curves on a mountain. So think of this as you go this way, you climb up the mountain. This is the altitude, yeah? Okay? So now, in order to get a high spectral efficiency in the cell, we want to be up the mountain somewhere here. Yeah? We need 2 things. We need large number of antennas, but that's not enough. We simultaneously to that also need long channel coherence so that we can squeeze in enough pilots such that we can train enough terminals that we multiplex to. So an important lesson in wireless comms in general, and MIMO in particular, is that the acquisition of channel state information is very often the limiting factor. I mean, any numerical results with perfect channel state information, well, if you have no mobility whatsoever, so very, very long channel coherence might make sense. But in general, anytime you're aiming at any sort of simulation or numerical study of any system with significant mobility, then channel state information is going to be the limiting factor. And I think this graph here brings that, hopefully, that point also home somewhat quantitatively. Yeah. All right, great. So let me see what I have here. I need to check a bit on my slides. Yeah, okay, good. So there's a final thing I'd like to talk about, and we will still stay with a single cell, and that is the fact that these formulas that I sketched here for capacity in the uplink and downlink, and for maximum ratio and zero forcing, where was that? Here, yeah. These formulas, not only are they clean and simple to work with, but also they are excellent predictions of what we can achieve in practice by using off-the-shelf coding and modulation techniques. In fact, I was asked a couple of years ago to give a tutorial on massive MIMO to an industrially oriented audience. And they asked that, it would be great if you could come and speak for an hour or 2, but please do not talk about all these closed form expressions. And then I went back home and said, hey, let's do a little simulation exercise. Okay, we pick off-the-shelf QPSK modulation, we pick some channel code, and we see how well it performs, and we compare to these closed form expressions. So that's what we did, okay? This is uplink, 100 antennas, 30 terminals, maximum ratio processing, QPSK modulation, rate 1/2 coding, that's an LDPC code off the shelf. Ricardson or Banke optimized design early 2000 sometime. Yeah, you do the math, 30 times 2 bits, that's 60. Times 1/2, that's 30. So we have some spectral efficiency, 30 bits per second in hertz. Yeah. Channel estimation through MMSE, the usual stuff. Fast mobility, so 200 samples coherence. And in this plot here, this is the bit error rate after decoding. It's a function of the SNR. 1,000 bits, 10,000 bits, 100,000 bits, always goes like a waterfall, okay? So, with coding and ergodic channel. And then we went back to the papers. Actually, this formula is equivalent to the one I had on the earlier slides. This is a little different notation. Apologize for that. So we took this spectral efficiency formula, and we equated it to 30 bits per second per hertz. And then we solved for the signal-to-noise ratio that we would need to get 30 bits per second per hertz, okay? That turned out to be minus 13.9 dB. Minus 13.9 dB, that's the red line here in the curve, okay? So this is the Shannon limit. This is the closed form capacity bound, yeah? So, in fact, several things we can learn from this graph here. One is that that capacity bound that we have in closed form comes extremely close to what off-the-shelf coding and modulation techniques offer us. So that means, first it means that actually there isn't a huge room for improvement in terms of designing other channel codes than using the Ricardson-Urbanke optimized code for AWGN channels 15 years ago. I mean, coding theorists could still squeeze this gain, particularly for shorter gains, but there isn't like order of magnitude improvements possible. Another lesson learned is that, in fact, I mean, these are codes which are designed for the AWGN channel. And we have a massive MIMO system. And still, those codes work pretty well. So that teaches us that the effective channel that every terminal sees in massive MIMO is pretty close to an AWGN channel. And that, again, is a consequence of the channel hardening, the fact that this effective gain fluctuates only slightly around its statistical mean. A third thing that we can learn is that, I mean, since these bounds are so close to what you get in an actual link simulation, there isn't a great deal of need for link simulations, in fact. I mean, these bounds are eminently useful not only to predict performance of systems, but also for the design of power control algorithms, for example. And I think even in retrospect, I mean, this is extremely beautiful, the fact that, you know, such clean and simple expressions gives us such accurate estimates of actual link performance, accounting for all the important effects that include mobility, channel estimation errors, interference, gain uncertainty, and so forth. Yeah. Great, any questions? Yeah. Okay, so that was about single cell. With multiple cells, interference becomes an even greater problem. And with multiple cells, there are two kinds of interference. There is non-coherent interference that comes from cells that use different pilots. And that interference pretty much looks like extra white noise. And then there is coherent interference. And coherent interference stems from a phenomenon known as pilot contamination. So here's what it means in practice. Okay, so suppose I'm the base station in my home cell. And I'm trying to learn the channel to one of my terminals here. And that terminal sends me a pilot sequence, okay? And I'm listening to the pilot sequence, I estimate the channel. At the same time, there's going to be somewhere else in some other cell that uses the very same pilot at the same time. And when he transmits at the same time, then effectively, I'm going to learn a linear combination of the estimate to my terminal and to the terminal in the other cell that used the same pilot. So later on, when I use the so obtained channel estimate to perform beamforming, then I'm going to create, wow, what was that? All right, great. So sorry about that. Happens here. So then in the downlink, we're going to use, you know, I mean, I'll be effectively learning a linear combination of the channel to my own guy in the home cell and the guy in the other cell who uses the same pilot, right? So when I subsequently use that estimate for beamforming, I'm going to create directed interference that points, I mean, that's beamformed precisely onto the guy who used the same pilot. That is known as pilot contamination. So now the good thing is that just like there are performance expressions for single cell, there are also performance expressions for multi-cell, massive MIMO. And these are all available in closed form, have the same interpretation as in the single cell case, namely that capacity is bounded by log 2 of 1 plus an effective SINR. That effective SINR looks something like this. This is all in our book. I mean, there's no point in trying to... Actually, if you work enough with these formulas, you'll remember them because they have a lot of structure, but there's no point in like blindly trying to memorize them, obviously. And these formulas here, they not only are actually, in fact, quite clean and simple, but they importantly account for all major impairments and effects that we have in a multi-cell system. That means interference within the cell, interference from surrounding cells, pilot contamination, channel estimation errors, and so forth. So looking at these, I mean, there are 4 cases, uplink and downlink, and maximum ratio and zero forcing. These formulas are quite similar from case to case. I mean, they have this kind of the same general structure. Yeah. Look at the all rational functions, and if you look at the numerator here, you see there is m and m minus k, just like we had in the single cell case. there is an SNR, there is a gamma. But now this gamma here is a multi-cell gamma, so it's not the one on the board. It's a little more complicated formula. Okay, I might write it later, but not right now. And there is eta LK. The eta LK is the power control coefficient used by the kth terminal in the Lth cell. Okay, so upstairs here is all good stuff, and then downstairs here is the one is for thermal noise. Yeah. And then we have non-coherent interference, and that will be these two first terms here. These are some pretty much over all the cells except for the, including the home cell indeed. And there will be path losses, there will be gammas and so on. And then there will be the last part down to the right here. This is coherent interference. That's a direct consequence of the pilot contamination. Yeah. So you can see that the bad thing here is that this coherent interference, it scales. You see there's an M here, an M minus K. So the coherent interference will get an array gain, just like the useful signal. Yeah. If you remember, if you back up to the, where was that? The formulas for single cell. No. Here. For single cell, then we pretend that we just keep on increasing number of antennas, M. Yeah, we do that. You see, there's no limit here. This will go to infinity eventually. Yeah, yeah. But in the multi-cell case, because there is something here in the denominator that also scales proportionally to M. If we let M go to infinity here, then eventually performance is going to saturate. So that's a consequence of the pilot contamination phenomenon. So in fact, pilot contamination here has two distinct effects. Yeah? One is that we get this coherent interference term here that scales for number of antennas. And the other effect is that this gamma upstairs here in the numerator, that gamma is much smaller than it is in the single cell case. Okay? And pilot contamination is an important effect. It's all captured in these formulas here. And however, in practice, a good way of keeping it under control is to reuse pilots more sparsely. So the family of pilot sequences that we have in the home cell are not reused in every other cell, but more sparsely, like frequency planned, reuse 3, 4, or 7 or something. Okay. And the effect of that is that we're going to push down these gammas. Remember, these gammas are related to beta, so they're related to the path loss. We're going to push those down so that the coherent interference term here is not negligible, but it's small, enough that it's not a major impairment anymore. Okay, so yes.
Power control in this formula is done per cell, not coordinate.
No. Okay. So that's a good question. In order to, the eta LKs here, those are power control coefficients that have to be appropriately selected. So I think that's an open. How to best do that in a multi-cell system? That's an open problem.
But
There,
with this formula, are do these formulas work for coordinated power control?
doesn't matter, how you do the power control. These formulas are valid regardless of the actual power control policy that you implement, okay? These formulas give you performance for a given set of coefficients, eta, LK, and that's it. Yeah. Yes?
Would you say that the behavior you observe in these models would scale also to other channels?
I'm sorry, I couldn't hear you.
The behavior you see from these equations, would you say that they scale also to other channel models? Because you said before that even though we have different channel models, the behavior is the same.
Yeah, okay, so the question is whether, this is all again for independent Rayleigh phase. The question, I guess, is whether, conclusions you draw from this set of formulas would hold if you had correlated Rayleigh or something else. I think that'll be a topic for the afternoon. Emmy looks like he's smiling. He's gonna, entertain us for 3 hours with correlated Rayleigh. So maybe I should just relegate the question. But I think the short answer is yes. The general insights that we learn here, those are quite universal. But then, of course, if you're gonna do like rigorous analysis under other models, you're gonna get a different set of formulas, and those are gonna look. Those are just gonna be harder to work with. So, but you can learn a lot here, which is universally valid. Yeah. All right, great. So massive MIMO gives us highly improved cell edge coverage. In a nominal system, you're going to be limited by noise, very likely, and then if you increase power, eventually you're going to be limited by interference. Increasing power is equivalent pretty much to densifying the network, right? So increase power, you increase the useful stuff, but you also increase interference. In contrast, in massive MIMO, because the useful power here scales with M, but the interference doesn't, assuming that we have sparse enough pilot reuse patterns so that this coherent interference is negligible, then the effective SINR scales proportionally to number of antennas. And that has the consequence that the SINR, even at the cell border, is increasing a lot, and that's what gives us the cell edge coverage. So, I mean, that's, intuitively speaking, because you scale the useful power with M, and interference is independent of M, and that comes very beautifully out from these equations that we sketched here. Yeah. Okay. I think in the interest of time, I'm not going to be able to walk through all this math here, but, those are interested, we can talk in the break. Yeah. Yes.
You said that the formula we have accounts for the errors in channel estimation.
Say again?
You mentioned that in the formulas we had, they account also for the errors in channel estimation.
That's correct. All the formulas here account for channel estimation errors. I mean, pilot contamination is one aspect of that, obviously, but yes, the formulas do account for channel estimation errors. That's the important fact of the whole analysis.
Do we have to have a prerequisite of having the channel hardening to say that it's...
No, you don't. I mean, the assumption here is that you have independent Rayleigh fading. And that in turn implies channel hardening. However, there is no reliance on channel hardening in the analysis. In fact, the deviation between the effective gain, which is random, and its statistical expectation, that deviation is accounted for in the analysis. In fact, that's what gives you, that in fact that is the reason for why, remember we had the sum over all k in the denominator, even including the terminal of interest, and that's why that appears down here. All right, great, so power control. Power control is extremely important in massive MIMO, in fact in any wireless system. To give everybody good service, to reduce the near-far effect. And that's particularly important for maximum ratio processing, where you have, you could have terminals close to the base station and generate a lot of interference, and you need to deal with that somehow. Depends only on the large-scale fading coefficients, so not on anything that varies on a fast time scale. And therefore, all these power control coefficients are recomputed only when the large-scale fading changes. I think I spoke of this earlier already, the fact that this effective signal to interference and noise ratios, these are rational functions of the power control coefficients. And that simplifies life a lot. Since we're rational functions, this means that you write any sort of inequalities you write with these SINRs, those inequalities are going to be linear functions of the etas, and they'll be very convenient to play with. Here's an example of that. Suppose you wanted to constrain your SINRs to be greater than some predetermined target like this, then that's going to give you a bunch of linear inequalities to play with, linear inequalities in etas. And those can be solved through any favorite linear programming solver. You just plug them in there and get going, and that's it. And that's true also in the multi-cell context, although you get more indices to keep track of. Okay, so it might look a bit daunting the first time you see these formulas, but fundamentally they are quite simple. And the important take-home again is that they are linear inequalities, so you can play around with linear programming any way that you want here. So the kind of canonical or the most tractable approach to power control in massive MIMO is something known as max-min fairness or max-min quality of service fairness, okay? And the philosophy behind max-min fairness is that you want to give everybody within a given cell the same effective SINR. No matter that terminal is close to the base station or is at the cell border or moving at maximum mobility or anything, you want to give them guaranteed the same quality of service, okay? And when trying to do this, there are pretty much three cases of interest. You can either do this, play around with just a single cell and ignore everything that happens, surrounding that cell. Or you can apply this philosophy in a multi-cell network. When you play around with a multi-cell network, there in turn are a couple of different ways the maximum fairness can be approached. Yeah? One way would be to enforce maximum fairness network-wide. To say that I have a network with 100 cells or 1,000 or 1,000,000 or something, and I want everybody, every terminal, every cell enjoy the same effective SINR. That does not work. The reason it works is that due to randomness in shadow fading, there's always going to be some terminals that drag down, that have very poor path loss, right? And if you try to satisfy, there's going to be somebody who is the worst. If you try to satisfy that somebody is the worst, then that terminal is going to drag down everybody else. So that does not scale, so don't do that, okay? A better way is to do maximum fairness power control within every cell. Yeah, you could, for example, postulate that every cell should operate autonomously. Base station in every cell should spend full power. At least one terminal per cell should spend full power. And then you do maximum fairness power control within every cell, but from cell to cell, the resulting SINR might vary. So that is really the preferred approach, and I'm not going to be able to do in detail because there's a lot of mathematics involved, but it's all done in our textbook, of course, and we can talk after the break. Also importantly, in practice, when you do power control, you're going to have to drop a couple of terminals from service. Typically, 5% is a target where people think is acceptable. That 5% of the terminals, they just don't get service because their shadow fading is too poor. Okay, and it depends on the shadow fading model. But if you believe in this canonical standard log normal model, then 5% is a good point where you want to cut the tail of that distribution. Just say that 5% of the terminals in every cell we just disregard from service, and then we serve everybody else there with uniform quality of service with this maximum fairness approach. So maximum fairness is nice because the math plays out quite neatly. In particular, in single cell, the maximum fairness power control coefficients are available in closed form. The resulting effective SINR is also available in closed form. And again, there are 4 cases. I just show one of them here, uplink zero forcing. The others look a bit the same, but a lot of indices and stuff to keep track of. So the important thing is to remember is that you can find these in closed form for a single cell. Unfortunately, for the multi-cell, it's a little, I don't know, it's a little harder. I mean, let me see what I can. Yeah, it's a little harder. I don't have them here on the slides because it would just be too much of detail to teach in one single morning, but you can find all that, of course, in the book. So, take-home point, power control in massive MIMO is a slow activity. Coefficients recomputed only when the large-scale fading changes. Maximum fairness is particularly attractive because it gives us this uniform quality of service that we, as operators, would be aiming for. And if we do that, we have to do it independently from one cell to the next because network-wide maximum fairness would not scale. So I'd like to round off. I think, 15 minutes. Is that correct, Hank? So is 1 o'clock a sharp limit, or? Yeah, pretty sharp. Okay. So thank you, by the way, for being so interactive. I really enjoyed all the questions, but I also ran a bit late here, so I'm sorry for that. But it should be okay. I should be able to wrap up here. So I'd like to use the remaining 15 minutes to talk a bit more in depth about case studies. And I have 2 case studies that I'll be presenting. The first is a single cell, isolated cell that provides rural broadband access to homes, okay? And the second case study is a multi-cell mobile access deployment in a dense urban environment. We have in the book a third case study, which is suburban deployment, but I won't be covering that here. So in these case studies, we have a standard set of parameters that are going to be common. We have a 20 megahertz bandwidth, we have a base station with omni gain, we have 9 dB noise figures, we have 300 Kelvin temperature, and we have log normal fading with 8 dB standard deviation, okay? So nothing really controversial there. And obviously, to do any sort of serious case study, you would have to do a link budget calculation pretty much along the lines of any of the standard textbooks in wireless comms, where SNR is the uplink power plus the gains, of the antennas minus the noise power, and you would have to work out the noise powers through the Boltzmann constant, and that's then that formula for the N naught watt per second and hertz. So we'll start with a rural broadband. So the vision here is that we have like some isolated town on the countryside, and we have 3,000 homes that we want to serve with mobile broadband in a 20 megahertz bandwidth. And we have 800 megahertz carrier, 11 kilometer cell radius. We want to cover everybody. The terminals have a slight antenna gain. They are stationary, so in principle we have like infinite channel coherence, but in practice, I mean, there's always going to be some objects that move, right? You're going to have trees that sway in the wind, for example. So we just put 50 milliseconds here, somewhat arbitrarily. Some diversity against the shadowing, second order. You could think of that as, you know, you mount a fixed antenna somewhere. You could try some different locations and pick the best, right? So it seems reasonable. HATA model, base station on a tower, and radiated powers, which are in total very low here, okay? So here is, I think, a sketch of the, I mean, not a sketch, in fact, it's a rigorous simulation of how many antennas that would be needed at the base station to offer, did I say here the, let's see, did I say that? I don't think I did, in fact. Yeah, I don't think I did, but I should have done. Okay, so there is a target spectral efficiency here as well. Which is, for the rural example, it's 20 megabit per second, and home for the downlink, and it's 10 megabit per second for the uplink. Okay, so the question is, how many antennas at the base station do we need in order to accomplish this? And we have 3,000 homes, so we could not get away with less than 3,000 antennas. And in fact, with zero forcing processing, with 95% probability, we would be getting away with something like 3,000, maybe 3,200, I think, with an uplink power of 1 watt. So it's a pretty compelling deployment example for fixed access using wireless. And similarly, we can look at the power that we need to radiate in the downlink for different antenna configurations and different uplink powers. And the take-home point really here is that we would, you know, need not more than 10 watt of power in total on the downlink with very high probability, so 95 or 99% probability, assuming we would select here 3,200 antennas and sufficient power in the uplink. So pretty exciting example. I mean, this might not happen for 5G, might not happen, you know, like in the next 5 or 10 years, but I hope to see it happen during my lifetime. I think it's like a pretty nice, bit more futuristic deployment example of massive MIMO, where you have thousands of antennas that serve thousands of terminals, and they're all stationary, right? And you could, you know, enable fiber-like access to places that don't have prior infrastructure for getting this broadband to the homes. Yeah, a little bit power control, skip that. So, okay, so the second example I have is on mobile access, and that is more, say, a 5G spot on, you know, case study. So in mobile access, in a multicellular system, so we have here a network, cells. And when you do this sort of system simulations, you have to be careful. I mean, hexagonal models are quite neat to deal with. Not that cells in general would be hexagonal, but they are pretty close to circles. And hexagonal networks have a regularity in their pattern that enables efficient implementations or wraparound formulas, so that cells up here in the northeastern boundary of this cluster, they will you know, be neighbors of the cells down here to the southwest and so forth. So when you do this sort of multi-cell simulations, you want to be sure to implement this wraparound properly, so that no cell in this network is in an advantageous position with respect to others, and such that all the cells are statistically identical. And as I mentioned earlier, I mean, we would have to do pilot reuse, and these are illustrations. I think here is a reuse of 7. So all these cells with the same color use the same pilot sequences, and you can see that with the reuse of 7, then if this is the home cell, you have to go like 3 cells, 3 rings before you have somebody using the same pilots, okay? So in fact, where you use 7, you really push down pilot contamination a lot. And this is where you use 3, then you had to go like 2 rings out before you see somebody who uses the same set of pilots. So again, any sort of system simulation you're aiming for, you have to be very careful to model things properly, and particularly, this pilot reuse, but also you have these hexagonal cells and modeling wraparound. So think of this as like a ball or something where, this edge here osculates, or its neighbors with the southwest, and that border here is neighbor with that border, right? So, yeah. Okay, so in the mobile access then case study, we have a multicellular system. We are at the 1.9 gigahertz carrier. Cells are a little smaller now, 500 meters. There are 18 terminals per cell nominally, which means that we drop 18 terminals at random, in every cell. However, a particular terminal is not necessarily served by the base station in that cell. Every terminal is served by the base station to which it has the best path loss, okay? So there's some kind of macro diversity effect, you can think of it like that, 95% coverage probability, which means that we a priori drop the 5% most disadvantaged terminals, don't attempt to give them service. No gains of the antennas, high mobility, cost channel model, base station on a tower, 1 watt in the downlink, in total 200 milliwatt in the uplink per terminal. And what else? Okay, so here are some results. These are 4 plots for uplink and for the downlink, for zero forcing and for maximum ratio. And these are cumulative distribution functions of the minimum throughput in any of the cells, okay? So in the sense that we apply this maximum fairness power control within every cell, subject to the constraint that every cell, every base station uses its maximum permitted power. And at least 1 terminal per cell uses maximum power, And then with a maximum fairness power control within every cell. However, that maximum achieved SINR might fluctuate from cell to cell. So this is a CDF over the so achieved maximum SINR performance. And what's of interest to look at here is what we can guarantee with 95% probability typically, okay? So to look at that, we have to look at the percentile here at 5%. And a couple of things we can learn here. One is that, in fact, it doesn't make a huge difference if we look at zero forcing or maximum ratio. Okay, the curve's a little different, but not vastly different. That's pretty much in line with what we have argued earlier. Okay. Another thing to learn is that if you look at the 95% likely value down here, you're going to see it depends a lot on which pilot reuse pattern we apply. In fact, with pilot reuse 1, that means reusing from every cell to the next. That's a very, it's not 0, but it's pretty low. Okay. And then I think here in this dense urban, the best pilot reuse is like 7, so pretty sparse reuse of the pilots. And then we end up with a 95% likely minimum quality of service performance of something like 3 or 4 megabits per second in its bandwidth. So really, I think a quantitative take-home point here is that obviously you can look at the actual number for the 95% likely, but it's also important to see that the pilot reuse factor makes a great difference, which means that pilot contamination is a very real phenomenon. Okay, it must not be ignored in the system design. However, by appropriate pilot reuse, we can not do away with it entirely, or we can push it down. I mean, this reuse 7 is really a lot far out to the right as compared to the other reuses here. So in fact, I don't know if there's any like even more sparse reuse. They could probably with a more sparse reuse, it would just cost too many resources to maintain orthogonalities. You want to do that. So probably you can say that 7 is optimal. Another lesson is that power control is extremely important. Okay, these are the same set of graphs, but now showing CDFs for different power control policies. And I mean, time won't allow me to talk about this in detail. Other than that, I can say that, you know, might be tempting to play around with very simple power control algorithms. Like you put all these coefficients equal, right? Or you do some kind of inverse SNR, inverse path loss power control. That works extremely poorly. In some cases, ignoring multi-cell interference can work. Most of the time, it doesn't work well. Network-wide maximum fairness is a no-no because it doesn't scale. It might give you reasonable, you know, performance if you have a small toy example with 3 cells, but it doesn't scale, so don't do that. And the algorithm that uniformly outperforms every other scheme here is the intracell maximum fairness. That it's too complicated for me to go through. It would take like another 3 hours, but you can read in the book, okay? And that is, let me also underline, this is not optimal, okay? This is pretty good. This is the best I know of. It's pretty good. However, it's not optimal. I mean, this is a ripe topic. Anybody who wants to write, you know, solve open problems in massive MIMO, I think multi-cell power control is a pretty good topic to work on. In fact, I think some people in the audience might already be onto that. So that's an important point to bring home here. Yeah. Okay, great. Yeah, okay, for those teaching, you might enjoy looking, you know, this is video you can go to. We built, I mean, our students built a reciprocity-based acoustic massive MIMO demonstrator to show and to teach these principles with estimation in the uplink, beamforming in the downlink. And yeah, this is all available. This is video that we recorded on YouTube for those that want to watch it. So great. And yeah, research problems. I think Emily is in fact going to talk about that in the afternoon, so I'll have to wrap up here. And the source of material for my lecture this morning, of course, is our textbook, the Cambridge textbook. Those who want to browse it, I have a copy here. I also have a discount coupon that I'll be happy to hand out. And with that, I really enjoy teaching this lecture. I hope that you learned a lot. I learned a lot. So thank you very much for coming.